Welcome. Let us continue with our formulation here of mass flux. So, mass flux and molar flux. Earlier we looked at velocities and now we are going to look at the fluxes. The mass flux of species I with respect to stationary coordinates is nothing but rho I, the product of the density times the velocity. Okay. The symbol that we are going to use is Ni. It is a vector because it has direction, both magnitude and direction. Therefore, the mass flux of species I represented as lowercase Ni is density times velocity. We have also already seen that density times velocity is the mass flux. We will call this equation 2.1.2-1. The molar flux of species I with respect to stationary coordinates, I may not say this all the time, but with respect to stationary coordinates, we are going to represent as capital Ni. So, capital Ni is nothing but concentration times the velocity. Okay, Ci times this is the velocity of the species I. 2.1.2-2. We said that we are more interested in the relative movement. Therefore, the relative mass flux of species I relative to mass average velocity, we are taking the mass average velocity to compare it with, that we represent as lowercase j I is rho I times the diffusive velocity V I minus V. Okay. This is the mass average velocity V and we have taken the difference here. Therefore, the diffusive velocity times the mass gives the relative mass flux of species I relative to the mass average velocity. 2.1.2-3. The relative molar flux of species I relative to the mass average velocity is represented as capital J I, and that is nothing but concentration times the velocity difference V I minus V. Okay. Again, the average with respect to mass average velocity, or the relationship relativity with respect to mass average velocity. 2.1.2-4. Only a couple more. These are the standard ones, so I am listing them all together, and these are rather simple. Flux is nothing but density times velocity, molar flux is nothing but concentration times velocity. Here it is only a diffusive aspect or the relative mass flux that we are looking at. Now, the relative mass flux of species I, but in this case relative to molar average velocity is going to be capital J I. No, this is lowercase j I star, that is rho I times V I minus V star. 2.1.2-5, and the relative molar flux of species I, this is relative mass flux, this is relative molar flux of species I relative to the molar average velocity is capital J I star time equals C I times the diffusive velocity with respect to the molar average velocity. 2.1.2-6. We are going to use these frequently, some of these frequently, I think I have listed, yeah. The commonly used fluxes are the mass flux, the molar flux capital Ni, the relative mass flux lowercase j I, and the relative molar flux uppercase J star. Okay. These are the ones that we will commonly use in this course. There are various other bases on which you can take relative fluxes on a molar basis and so on and so forth. If it is necessary, you can always go and pick it up from other books, or you can just extend this formulation to other things. We won't be using those fluxes much, and therefore I have not listed them here. There are many other bases on which you can take the relative fluxes, mass fluxes, molar fluxes, and so on and so forth. We will not get into that in this course. Now, let us consider equation 2.1.2-6, which happens to be the relative molar flux expression C I times V I minus V star. If we substitute for V star using the definition of V star, then V star is nothing but Ci V star is nothing but sum of Cj Vj divided by the sum of Cj. Here, if you remove the brackets, Ci Vi minus Ci times V star, therefore the Ci comes here. And from the definition of mole fraction, concentration divided by the total concentration, this, you could write this as Xi, and this is nothing but capital Ni, molar flux, right? Ci Vi molar flux equals Xi times sum over the molar fluxes of the other components, J, all the components, that is. This is 2.1.2-7, or the molar relative molar flux equals Ni minus Xi molar fraction. This is nothing but the sum of all molar fluxes, and that we are going to represent it as Nt. Nt is the total molar flux, and we will call this equation 2.1.2-8. Now, let us look at mass flux. The 2.1.2-5, which is this lowercase j, this is lowercase ji, this is mass flux, right? Yeah, lowercase ji star because it is with relative to molar average velocity is rho I times Vi minus V star. And if you look at this, Ji is rho I Vi minus sum of rho j Vj divided by the sum of rho j, and because we have removed the brackets, the rho I comes in here. You can see where I am getting at. This is nothing but the mass fraction. So, from the definition of mass fraction, which is density, mass fraction is mass of I divided by the total mass. You divide above and below by volume, you get density of I divided by the total density, right? And therefore, Ji is Ni minus Wi times the sum over Nj of all the other mass fluxes, all different mass fluxes. We will call this equation 2.1.2-9, or Ji is nothing but Ni minus Wi times Nt. This is Nt, the total mass flux that has been written here. This is equation 2.1.2-10. Okay. So, these are some ways of these expressions will turn out to be useful. That is the reason I wrote these here. Let us continue. I think we've been at it for not too long a time, so we can continue a little further. We will talk about a constitutive equation. This is a different concept. We have seen conservation equation so far, the mass conservation equation. Mass conservation equation in the context of whatever we did became what is called the continuity equation. Okay. That is an equation of change. It tells you how the mass changes over time, and that is widely applicable, very widely applicable. The only riders that we put in is no nuclear conversions or no nuclear reactions, and no traveling at the speeds close to that of light. So, it is very widely applicable for most of our or almost all our applications. A relationship exists between the flux of the conserved quantity here and the material or the constituent properties of the system of interest usually. Such a relationship is not as widely applicable as the conservation equation. You cannot close your eyes and apply it, but it is applicable to a wide variety of substances or a class of similar substances, okay, and therefore, that turns out to be useful, and that is called a constitutive equation. A conservation equation, typically mass conservation, momentum conservation, energy conservation, charge conservation, and so on and so forth, are very widely applicable almost across the board, whereas a constitutive equation is a relationship between the flux of that of a conserved quantity and the material properties of the system of interest, that is not as widely applicable as a conservation equation, but it is still applicable over a wide range of substances, of similar substances. And since it is related to the constituent properties, we call it the constitutive equation. A combination of the constitutive equations or equations of state, a constitutive equation is the equation of state. Do you recall the equation of state now? Think about it. And conservation equation, equations of change. Constitutive equations, equations of state. PV equals nRT is an equation of state. And conservation equation, equation of change, the mass conservation equation, is useful in analysis and design of engineering systems. So, this pretty much is another base for this course. We are going to see this in various different aspects of this course, the combination of constitutive equations and conservation equations for each different case. Adolf Fick experimentally found the relationship between molar flux and concentrations in dilute binary solutions of non-reacting solutes. Okay. The conditions are important: relationship between molar flux and concentrations, dilute binary solutions, two components of non-reacting solutes. And he experimentally found this out first and came up with Fick's first law. Fick's first law in one dimension for a species I is nothing but the molar flux of I equals di times minus dci dx. Let me take the minus along with this where it actually belongs. Di times minus dci dx. Dci dx is nothing but the concentration gradient, the variation of concentration with respect to space, single dimension x. If this is Ci, you could write it in terms of the mole fraction, right. So, C times Xi is Ci, C is a constant, the total concentration is a constant of all the species taken together, and therefore, you can bring it out of the derivative. Therefore, you can write this as minus C di dxi dx. Note that this is mole fraction, this is the x dimension. Okay. There is a possibility of a confusion here, do not worry about it. Dx of xi, the variation of with respect to x of the mole fraction. This is an important equation, the constitutive equation, Fick's first law, which relates the molar flux with the concentration in dilute binary solutions. We will call this equation 2.2.1-1. This di, the capital Di, is called the diffusivity of I in the mixture. Okay. This, although written for binary solution, you can extend it to multi-component mixtures also. That is the reason I put in a di here rather than a dab or something like that, to generalize it to a multi-component mixture. So, di is the diffusivity of I in the mixture. The species I moves relative to the mixture in the direction of decreasing mole fraction of I. Okay. That is the reason why there is a negative here. Okay. The flux is proportional to the negative of the concentration gradient. Yeah, that is what is given here. Mass flux is proportional to the negative of the concentration gradient. In general, any flux is proportional to the negative of a certain gradient. That is what it will turn out to be, and we will look at them one by one as we go along. This gradient is that of the primary driving force for that flux. Okay. In this case, you have the concentration gradient. The concentration gradient is proportional to the flux, or the flux is proportional to the concentration gradient. That is the way to look at it in terms of independent and dependent quantities. And this concentration gradient happens to be the primary driving force for the mass flux. In 3 dimensions, this is only one dimension. We are looking at general formulations in this course. In 3 dimensions is as practical as we can get, practical and as general as we can get for our situations. You could replace the derivative here, d dx, with a del, right, with a del there, capital J I star equals minus C d I del x I, okay, because it gives you the gradient in 3 dimensions, 3 directions. 2.2.1-2. Now, if you substitute 2.2.1-2 in 2.1.2-8, which is this, J I equals N I minus X I N T, we get minus C d I del x I, this is J I, equals N I minus X I N T, equation 2.2.1-3, or N I, okay, I am writing N I in terms of the other things, just take this to the other side, minus C I d I C d I del x I plus X I N T, equation 2.2.1-4. This is the component due to diffusion. This is the total flux of I in a certain case. This is the component due to diffusion, the molecular motion, and this is the component due to fluid motion, convective motion, or the bulk motion. Okay, recall stirring of your tea, coffee, the sugar in your tea or coffee with a spoon. That is a fluid motion, convective motion, or bulk motion. These are terms that we are going to use to represent that stirring equivalent. Let us see the fixed law written in terms of mass fraction instead of the mole fraction. Okay, you could do that either way. So, you can actually derive this. I am just going to say this: J I equals mass flux of I equals minus rho d I del of W I. This is mass flux and this is mass fraction. That is mole flux and mole fraction. This is mass flux and mass fraction. You can actually derive this at 2.2.1-5. Why don't I let you derive this? If you run into difficulties with this derivation, then get back to me, send me an email. I will tell you how to do it. This is a few steps and it is good for you to go back. It is just definition and you substitute the various definitions and you will get from there, starting with our fixed first law in terms of molar, in terms of mole fractions. If you start there and replace various things in terms of masses, you will end up here. Okay. Why don't you try this out? Now, if you substitute 2.2.1 in 2.1.2-10, which is J I equals N I times minus W I N T, we get, J I we are replacing by minus rho d I del of W I equals N I minus W I N T. Equation 2.2.1-6, and this, all these are useful expressions. That is the reason why we have derived this, and how it will turn out to be useful we will see in the later courses or later classes of this course. I am going to leave this as a reading assignment for you. What these reading assignments do is they will expand your understanding, make them more complete, and so on and so forth. Most of them will be from the textbook. However, given the access, I am not going to make that compulsory. In other words, you won't be tested on those for people who are worried about being tested and so on and so forth, which is a very common concern. You won't be tested on these reading assignments here, but it is good for you to understand the material. So, go find the book and read this. What I would like you to read from the book is Fixed Law for Concentrated Solutions. Recall that the earlier formulation of the Fick's law, all these are for dilute solutions. That is what Fick did. And in our biological case, you would very rarely find dilute solutions. Most of them will be concentrated. And you could come up with a slightly different formulation for this for concentrated solutions in terms of chemical potential. And that is given in section 2.2.1.1 in the textbook. Go and read that, please. Okay. I think we will stop here. Yeah, we are at the end. We will stop here for this lecture and continue in the next lecture. See you then.